Hello everyone. We're going to continue with section 8.2 about hybrid atomic orbitals. The learning objective for this video is determine the hybrid orbitals associated with various molecular geometries. So let's go ahead and get started on that. So we ended last time by discussing these important ideas in terms of understanding hybridization. So make sure you feel comfortable with that before we proceed to look at some specific examples. The first kind of hybridization we'll talk about is sp hybridization. So the idea here is that you combine an s orbital and a p orbital to make a new type of orbital. And because you're combining two orbitals, you'll end up with two hybrid orbitals. And we'll see how we can apply this to something like, say, beryllium chloride molecules. So here we're showing the hybridization. So we have an s orbital and we have a p orbital. When we combine them, we get these two hybrid orbitals. So what you'll notice about them, and this is true for most hybrid orbitals, is that they're not symmetric the way that the atomic orbitals were symmetric. So what we're showing here, it looks sort of like the p orbital, except that you have a larger lobe and a smaller lobe, and then you have kind of two of them where you're switching the location of the larger lobe. So these are the hybrid orbitals when we combine an S and a P. So what this ends up with is we end up with a linear arrangement. So we have one of the larger lobes pointing kind of one direction, and then the other larger lobe pointing 180 degrees in the opposite direction. So we're showing that here. So this is not showing a p orbital. It's showing two sp hybrid orbitals. So this is sp hybridization. So when we have sp hybridization, we end up with linear molecules. And so we can see how it's consistent with VSEPR theory. Here we're showing what this looks like in terms of if we were to draw the electron configuration. So prior to the hybridization, on the atom by itself, we would have two electrons in an s subshell, and then we are taking that and combining it with one of these p subshells, and we are left with two p subshells that are, we say, unhybridized. So they are the same as what they started with over here. And then when we combine them, we end up with something that's partway between the energy of an S and a P. And so the hybridized orbitals that you come up with are higher energy than they would be if it was just an atom by itself. So this is why the atoms don't do this, because it is something that's a higher energy. But when you then combine that to form a bond, you get something that would be a lower energy than it would have been by itself. So that's kind of the idea of hybridization and applying it to an sp hybrid form. So this is the hybridization that we get when we have a central atom, one central atom, with two regions of electron density around it. So think back to VSEPR theory and some examples of that. You'll notice that some of these do have metals involved. So there are times when metals can behave in covalent bonding. Don't worry about figuring out when that is, but assume if you have a question around it, that's in module 7 or 8, then it probably is an example of that. Okay, the next type of hybridization we'll talk about is called sp2 hybridization. And so what's happening here is we have one S and we have two P. So P and then the superscript 2 is telling us how many we have there. Okay, so we're showing these are the atomic orbitals we're starting with, 1s and 2p's. You'll notice that the p's have different orientations here. And you don't have to remember exactly that it's an x and a y. That doesn't even really matter too much. It's just that you would want to know there's 1s and 2 that are p. And when we combine these together, we end up with these hybrid orbitals. One thing to note here is that we have 3 of them. So we had 1 s and 2 p's, so we'll end up with 3 sp2 hybrid orbitals because of the number that were combined to make that. So you'll notice we have 3 of them, and then in terms of their arrangement, we basically have them all in the same plane, and this is a little bit tricky in that we're showing them kind of aligning along the coordinate axes here. So it's not exactly like this. I think the best thing to look at here is that this is showing all 3 of them, and they're 120 degrees apart. So if we have one of them that is along one of the Cartesian coordinate axes, the other 2 will not be, because it's a 120 degree angle. So this is showing, basically 180 degree and then 90 degrees. So these angles are not correct here, but you basically end up with the trigonal planar arrangement where you have 3 orbitals that you have kind of the big lobe and the small lobe, and the big lobes are 120 degrees apart from each other. Okay, so this hybrid orbital leads to the VSEPR configuration that has bond angles of 120 degrees. Okay, so some examples here showing some additional pictures showing what goes on and where this might occur. Here we're showing how they combine again. So you have you might start with 2 electrons in the s orbital, 1 in the p orbital, and then the hybridized form, you have 3 that are sp2 and 1 unhybridized p orbital that's still left behind. And here are some examples of molecules that have this kind of hybridization. You'll notice we have a lot of double bonds here. That's often true with sp2 hybridization, but we'll discuss what the bonds have to do with that in a later video. What I should say, what the double bonding part of that. So we're only discussing a part of this here. We'll come back and talk about additional aspects of the double bonding part in a later video. Okay, and then we have sp3 hybridization. This one is very common because we have 1s and 3p, and that's all, that's if we have, all of the possibilities. So you're combining all of them together, all 4 into one thing, and you end up with 4 hybrid orbitals. And I think this one is doing a better job of showing kind of where they would end up than the sp2 was showing. And you end up with, if you look at all 4 of those orbitals at the same time, you end up with that tetrahedral arrangement that VSEPR theory would predict. Okay, so tetrahedral arrangements are often involved with things that follow the octet rule. So that's why this one is often pretty important to know about. Here we're showing how those combine. So you might start out with something that has 2 electrons in an s orbital, 1 electron in each of 2 p orbitals, and you combine this together, and you end up with 4 hybrid orbitals, each of them with 1 electron. Again, this is between s and p in terms of the energy. So it's a higher energy form, which is why it doesn't exist in neutral atoms, but then you would combine that with, when you form a bond with something else from the hybrid orbital, then you would get a lower energy overall. So here we're showing an example of how this would work. So this is showing ethane, which has this structure C2H6. You don't have to remember how to name that. Don't worry about that. But what we have there is we have you should be able to, if you're given C2H6, draw the correct Lewis structure for that, and then from that come up with what we're discussing here. So in this case, you don't have one central atom, you have two carbons each connected to each other. And you would recognize from the Lewis structure that you have 4 places with electrons. So you would have tetrahedral geometry, and you would then have sp3 hybrid orbitals. So we're showing kind of the sp3 hybrid orbitals here on each of those carbons. And then those sp3 hybrid orbitals are then overlapping with an s orbital on a hydrogen. So they do that, each one does that 3 times. And then also one of those sp3 hybrid orbitals is overlapping with the sp3 hybrid orbital on the other carbon. Okay, so this is showing how those overlaps occur to form the bonds in C2H6. And these are all going to be sigma bonds. So remember we talked about sigma bonds in 8.1. We're still using that terminology. In fact, as we'll see, the sigma and pi terminology becomes even more relevant with the hybrid atomic orbital concept than it was with the valence bond theory. So we have each of these bonds is a sigma bond. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 sigma bonds in this molecule, and they are between either sp3 and s, or in one case between 2 different sp3 orbitals. Okay, your book does talk about these additional hybridizations that would be consistent with things that don't follow the octet rule, so things with trigonal, bipyramidal, and octahedral arrangements. This is not something I would like to focus on. It's actually not something that people that do look at these kinds of molecules really consider in terms of what's going on. So we'll kind of skip over that. So don't worry about that too much. There might be some that come up on some of the homework or one of the lab activities. So you might look at it for that, but this is not something that will be on the quiz. Okay, so let's talk about the assignment of hybrid orbitals to central atoms. So we've gone through a number of examples here already, but I want to go ahead and kind of formalize this. So the first thing to do would be to determine the Lewis structure of the molecule. So you would do that first. If you're given the formula, can you find the Lewis structure? Then you would go through what we did with Vesper theory to find the regions of electron density around an atom. And when we do this, single bonds, multiple bonds, and lone pairs each count as one region. We could include radicals where we're not going to get into that level of detail for the most part. And then assign hybrid orbitals based on the geometry. So here we're showing kind of how you would go about doing that. So you can see how the different shape corresponds with a different hybridization. So everything that's tetrahedral will have sp3 hybridization. Everything that's trigonoplanar will have sp2 hybridization. Everything that's linear will have sp hybridization. Okay, so it's always going to work that way. Again, we won't do too much with these last two. One thing I want to mention here is that this model for for molecules works well in some cases, but not necessarily in others. And your book talks about some examples within even comparing oxygen and other atoms or other elements within its group of the periodic table, how it kind of changes and ends up maybe not working that well with this model. So just be aware that it doesn't work for everything, but it is one that works a lot for the things that we care about in this course. You'll notice we haven't talked about double and triple bonds too much here, but we'll discuss in the next video how we do that with the hybrid, how we account for double and triple bonds using the hybrid atomic orbitals model.